Hey, what's going on, guys? Let's do this problem right here. The question is asking, in a hydroelectric power plant, water enters the turbine nozzle at 800 kilopascal, absolute with low velocity. If the nozzle outlets are exposed to atmospheric pressure of 100 kilopascal, determine the maximum velocity to which water can be accelerated by the nozzles before striking the turbine blades. Turbine blades. Let's see how we can do this. So let's draw a diagram for this one. So we have this nozzle right here. So let's say this is the turbine nozzle, turbine nozzle, and it's entering, right? The water enters with 800 kilopascal, 800 kilopascal, and it's going out with the 100 kilopascal. This is the ATM. So 100 kilopascal atmospheric pressure. And then what else they have given? So enters and going out, and these are the information we have. And from this one we can determine that Z1, elevation 1, the height is going to be equal to C2. So that's one assumption, like we know this one for sure. And also they are saying this is going with a very low velocity. So here the velocity is like 0, very low. It means we can assume this is 0. So let's since these two heights are equal, we can take the Bernoulli's head equation. That will make everything easier because we can cancel these two elevations, right? So let's take the head equation. Head Bernoulli's equation. That is P1 over rho g plus V2 over 2g plus C1. In the other side, we are going to have P2 over rho g plus, this is V1, right? V1. And here we are going to have V2. That's the question. V2 is what we are trying to find. This velocity right here, maximum velocity. So V2 over 2g plus Z2. Since we have this information, the elevation is equal both sides, we can cancel this one. And also this very low velocity, entering velocity is very low, so we can, this is going to be zeros, the whole thing is going to be 0, so we can cancel this one too. So that one gives us P1 over rho g is equal to P2 over rho g plus V2 over rho g, right? And if you look at this, we have g in all of this thing, so we can cancel this g in all of these things. Let's switch this equation around because we have to find the V2. That's our question. So V2 is going to be equal to square root of V1 square, V2 square. So that is the equation, right? So this is going to be square root of 2 P1 minus P2. We can say ATM because outside, right? Outside is ATM. ATM over rho, the density of the water. So we have all the information right now. So let's plug all the values. Square root of 2 P1, this is 800 kilopascal. 800 kilopascal minus 100 kilopascal. Kilopascal divided by 1000 kilogram per meter cube. 1000 kilogram per meter cube, density of the water. Since it is kilopascal, I can cancel this one. This is going to be 1000 Newton per meter square over Pascal, right? If we convert this one. So since this, we can cancel this one right here. So that gives us 2 times 700, that's going to be square root of 1400. And this is, since this is Newton meter square, if you want to know the unit conversion, we know that Newton is equal to kilogram meter per second square. Since we have meter square right here, this will give us meter minus 1, because meter square plus, that's going to be minus 2, plus 1 minus 2 is going to be minus 1, divided by kilogram per meter cube. Kilogram cancels, you will get meter square per second square. So that gives us 37.4 meter per second, and that's the velocity it's going to go out, and that is what they are asking, right? And that's it. I hope you guys like this video. See you next time.